Thanks for asking. Yeah. Thanks for asking. We're short on salary. Excited for Thanksgiving? Yeah, I am. What about you? Yeah.
Oh, no, we're not. It's still not class time. Although we'll see who shows up in class.
Oh, okay. I was like, actually, I have a niece who's 18. We're doing sushi this year instead of Thanksgiving because everyone's sick of Thanksgiving. And sake.
Sake?
Yeah. My parents would always let me have Christmas and stuff. I love sake. Well, that's really right. Some. But it's delicious. I have had hot sake it's like hot roast. No. The unfiltered is good. There's one that I'm gonna botch the name, it's like Gagacon or something like that. But yeah. It's the black bottle with gold. Yep. It's so good. Oh, it's expensive.
Yeah.
What do you think for I'm gonna a Corvallis and scout out where I'm I love Corvallis. I was supposed to move there this year. Already? Yeah. Decided community college instead? I decided I didn't want to spend. Yeah, that's right. I know, I'm like, how much are they going to charge me? We have it's crazy. Well, I gave you $200 which is really fun. Nice Christmas sweater.
Okay. Okay, Max, do you want to make an announcement? All right, Max has an announcement for us before we begin.
Hi, everybody. As you know, I am the president of the RCC Music Club, and today we are going to be having a music club meeting at 3:30. It's going to be down in room 119. If you guys can catch it, it would be awesome. We do little jam sessions after our administrative meeting. What the administrative meeting entails is just going over what we're going to do for the rest of this term, what we're going to do for next term, going over the budget, and nominating any new candidates for positions that we have open. We also have our holiday caroling and cocoa event coming up on December 4th. We'll be doing that at 5:30 and we'll go until 8 p.m.
Oh, where are you going to be caroling around?
Here on campus.
So like all around the buildings and stuff? Okay.
Because the whole school will hear us from the atrium.
Cool. Thank you. Any other announcements or anything? Yeah.
So I volunteer with Road Foods United, it's based out in Ashland. But every week they have a free farmer's market. And the Bedford one is down off the 99, like one light past the Grange. Anyone's welcome, you don't have to show any proof of need or whatever. And they have a bunch of fresh produce from local farms. So from 4 to 6, down over past the Grange, bring your own bags, get some fresh produce. Even anyone you know needs it.
Thank you for that one. Other announcements. So if you're in need of food too, I think you should have already signed up right with ASG for like the whole Thanksgiving thing. But again, reach out to me if you still need any help with Thanksgiving or anything, Christmas. Just talk to me personally. Happy to connect you with resources or figure out what to do. All right, and then, other things. So just where we are this week. Can you believe we're already at week 9? That's kind of scary. I know. So the no lab this week, of course. Thanksgiving, so enjoy your Thanksgiving. There's my horrible turkey. Yeah, I mean, at least I like drew it as 3 spheres instead of just the physics, like, we'll approximate it as a sphere, but I tried, okay? So enjoy the Thanksgiving. Where's the tail? I was drawing like a cooked turkey, but I know, maybe I should have made it like a real turkey. There we go, that's better. I'm sorry, I can't draw. And so that being said, if we do need to do makeups or anything, if you missed a quiz, makeups during lab time today. All right, let's dive into lecture then since, oh, wait, before we dive into lecture, some things I was thinking of. So while you're doing some maybe Christmas shopping, this should already be linked on our Blackboard, but I highly suggest you buy this little kit. So just someone was asking about next quarter, so that got me thinking about next quarter, but you also want to think about eventually taking OChem. And so this little kit, I call it the baby molecule kit, but this is my favorite organic chemistry kit, and so I would purchase this one. So for reference, if I Google organic chemistry kit, so a lot of the times what you're sold, well, these ones are okay, which you've seen. I was trying to find the other one that you find in lab or find sold in like bookstores, but it's kind of horrible. I can't find it right now, but it's terrible because you're like trying to click the stereo centers together and you can hear everyone in the exam like popping and unpopping that kit. Terrible. I like this one. The stereo centers are already there. I'll bring mine in next week so you can kind of check it out, but I would definitely purchase this one. You might have to look it up by the stock number, HGS, the 4010, but that should pull up the correct one you're looking for. And then I did link to next year's syllabus, so you could also kind of start reading ahead if you're interested in reading ahead over Christmas break. So we'll go back to geometry and then do MO theory, which I always say hang through MO theory because people either love it or hate it. And then we'll be back to kind of more algebra stuff if that is more your jam. All right, so let's look at solutions today. And this is kind of a good topic to shortchange. And I only mean that because it's kind of simple, at least mathematically. It is super important though, and I'll highlight the importance in just a second. And so solutions are just defined as homogeneous mixtures, and then they're made up of 2 or more chemical substances. And so we'll have the solute, which is usually called the minor component, and it's usually, right, what you are dissolving, usually the solid part. Sometimes could be a liquid, right? You could be doing a dilution, but again, usually solid. And then we dissolve it with a solvent. And in general chemistry, most of the time we see these AQ or aqueous solutions. So usually we're using water as a solvent. Once you move on to organic chemistry, you can have all sorts of things as solvent. Ether is a common one. Dichloromethane, as I previously mentioned, right, that used to be a common solvent, probably falling out of favor quickly. Benzene, toluene, blah, 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 pentane, so many. So we could go on and on. And so that's our solvent. And so kind of getting into some of the chemistry behind it. So again, I think people kind of asked these questions earlier, and we're kind of re-emphasizing that our solution formation is a result of interaction between our solute and our solvent. And again, when we had busted out the little sodium chloride, right, we said, okay, well, sodium chloride, we have a cation for sodium, anion for chloride, and then the water comes along, and starts to overcome, right, our solute-solute interactions, and so this starts to solubilize things. And so this also starts to get into these common sayings that we have, like dissolves like. And often we think of this with kind of polar and non-polar substances. So for instance, if you have an oil spill, right, so oil is very non-polar, so a lot of hydrocarbon chains. And so, well, traditionally now we're going to have a safety lesson. So usually people will say to use hexane, and so hexane is commonly used. However, there's a problem with hexane, is that it's toxic. And actually hexane itself is not toxic, but rather it's the your product right in your body. So once it takes the hexane and then it processes in your body, it makes like an alcohol that's at 6 carbons. And so that is just the appropriate length to mess up your synapses. And so if you were to be exposed to large amounts of hexane over time, you could have motor function issues. So don't liberally breathe in hexane. But like I said, most people would say to use hexane because it's nonpolar. So for safety reasons, we would use pentane or heptane. So both of those are appropriate substitutions. So the 5 carbon or the 7 carbon chain. And again, both nonpolar, so that can be used to clean up your oil spill. Or sometimes toluene is also used for that reason. And then looking at polar substances, so we can look at like water, and ethanol is of course a mixture. And those are both polar substances, so they will mix. And then nature has a tendency towards spontaneous mixing, and so this also has to deal with entropy. And I didn't bring the experiment, but I think most people have seen this, right? You could put a drop of food coloring in water and then let it sit there and it'll disperse throughout. So that is a reference to that. So just nature has a tendency again towards mixing. And then just looking at different types of solutions. So we can have, right, a gas-gas mixture. So obviously air is an example. So again, our air is about 97% nitrogen, and then the rest, right, oxygen, CO2, argon, other minor gases. We can have, right, a gas liquid solution as well, such as club soda or anything, right, that's carbonated. Any of our carbonated beverages, you can get CO2 in water. Or, right, sometimes now they have the nitro brews, so now you can have nitrogen as well, just anything pressurized. Liquid, so like we mentioned, ethanol, the one for consumption, right, the alcohol for consumption would be a mixture. Obviously, right, you don't buy 200 proof, so 200 proof would be the same as 100% alcohol. And that is a regulated substance, thanks to some chemists having too much fun in the lab after hours. But otherwise, right, vodka is a mixture of ethanol and water. You could also have solid liquids such as seawater, or like I mentioned, right, any of our reagents that we use in lab. And then solid, so we can have that as well with brass. So this makes a nice alloy, so copper and zinc. And at some point, remind me to do this demo for y'all. Usually I do this as like a magic trick for kids of turning copper into silver, right, with zinc, and then to gold with brass. And so that's a good magic show for the children. All right, so going back to solubility, so blah, 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 one substance, again, our solute dissolves in our solvent, such as salt. You could also dissolve bromine and DCM or another organic substance, solvent for that matter. And then I'm sure you all have seen this, again, with salad dressing, that oil is insoluble in water, and they make these immiscible layers. So, right, you get some sort of layering with the less dense substance on bottom. And again, solubility depends on, obviously, we have our tendency towards mixing with entropy, and then, right, you can also give something mechanical energy, right, putting it in, trying to stir it around, but then also dealing with the intermolecular forces, which we'll come back and take a deeper look at this, I think, second quarter, right, as we dive into more specifically our intermolecular forces. All right, so let's look into, well, how do we actually make these solutions? Because this is, like I mentioned, the super important and super practical part of it. And so we have our solutions are often just quantitatively described as dilute or concentrated. And right, again, it kind of just depends what people classify as dilute. For my general sense, I would say that less than 3 molar is kind of dilute, right? We're just kind of thinking of what is dangerous. So once it's less than 3 molar, it's kind of less dangerous. But obviously, right, you still want to be careful. And then concentrated solutions obviously have the danger, and this would be, again, anything greater than 3 molar, just roughly speaking. But obviously they have a larger amount of solute in there compared to solvent, but then also just other considerations of more hazardous. And so there's sometimes, right, storage considerations. So again, everything is stored in the stockroom, and it's in this closet that's all ventilated so that we can have, right, these concentrated solutions just sitting in there. So thinking back to like the 15 molar nitric acid, right, super concentrated. So that is kind of dangerous to just have sitting there, but that's why it's properly engineered with airflow control. All right, and so what if you wanted to make a solution? So we'll go over this example, and then we'll actually go over an example that happened today. And again, right, what happens on a day-to-day basis in the stockroom. And so let's look at this. And so most properly, we'd want to make a solution in what's called a volumetric flask. And so these volumetric flasks are only made for one measure, right? So in this case, this is a 1 liter. They come in 500 milliliters, right? 2 liters, all sorts of sizes, but it's just calibrated for one specific measurement. And so in this case, it looks like we want to make a 1 molar sodium chloride solution. And so that's what is done. And so first, right, they calculate how much a mole weighs. So there's the molar amount. And so then they weigh out 58.44 grams. Then you want to pour it in your volumetric. And then you want to add water, and just enough to dissolve it. And then at this point, once it's about like 3/4 or so full, you shake it up. And usually these things have a ground stopcock in there, so you could seal that up, shake it, shake it, shake it, and then continue filling it up to the proper mark. Again, you can't go over, or else you have to start all over again. It's inaccurate. And then once you get to the 1 liter, again, shake it, shake it, shake it, make it all homogeneous. And then you have your properly made 1 molar solution there. And so this is the most common way to express concentration. So there are other ways, but we'll just focus on molarity for now. And so molarity is defined as the number of moles per liter. So I would star this. Again, you'll want this relationship. And so think about molarity as just this, right? Moles per liter. And you can also think of using proportions later to figure out the answer to stuff. All right, so let's try this warm-up solution. And then we'll look at the real-world problem today. So try to start this on your own. So we're dissolving 25.5 grams of potassium bromide in enough water to make a 1.75 liter solution. So what's our molarity? So what do we need to calculate first? Good, so we need moles. Excellent. So how do we find moles again? So conversion factors. So what's our molecular weight of potassium bromide? You said 119.81, so grams per mole. Excellent. So now write conversion factor. So I'm just setting up dimensional analysis. You could also set up a proportion if that works better for you. All right, you just want to be comfortable mathematically. And so then, oh, sorry, I didn't pull up my calculator. I do see answer in the chat of 0.214 moles. Is that what everybody got? So I see some nods so far. And so then once we get our moles, right, then we just have to plug it in to the rest of our formula. And so again, slight discrepancies potentially. And then now divided by our volume, which does need to be in liters, and then they did give it to us in liters. And so now we can finish. So what's our molarity of our solution? So I see some nods. And then chat says it as well, so 0.122 molarity or moles per liter there. Questions on that one? So that was good. So let's do another one. So this was actually from the stock room today. So from the stock room. And so again, right, you know how they have everything. They have, right, the little dropper bottles. And so they found today that they were out of their stock solution that they used to refill. And so they have their stock 0.1 molar solution of iron chloride. And we want to use the hexahydrate form of the compound. And I only suggested using the hexahydrate for solubility reasons. Since it's already complex with a bunch of water, it should go into water a little bit more easily than the anhydrous version. And so let's say we want to make a 0.1 molar solution and we need 500 milliliters of this. So how many grams of iron 3 chloride hexahydrate do we need? So how would you start that? So try to start that calculation. So start walking me through this one. What did we find? What can we do? Any thoughts?
We can start with 0.1 mole there and multiply it by 500 milliliters.
So multiply it by 500 milliliters.
And convert that to liters.
Yeah, I would even set up like a proportion. So that's kind of what I was thinking, if that makes it easier for people. And right, so converting that to liters, then you could solve for x, or like you were saying, you could do some dimensional analysis. So okay, we have a 0.1 molar solution. Again, that's moles per 1 liter. So how many moles are in? Again, multiply it by 0.5, get rid of liters, right? And that'll give you moles. So either way, how many moles do we get of iron 3 chloride? Sorry, what'd you say? Say it loud. 0.05 moles. Good. So right, we're halfway there. So 0.05 moles of our iron 3 chloride hexahydrate. Good. And so now we just have to get the molecular weight of this. Does anybody have the molecular weight?
0.11 gram. Oh, of the overall?
Yeah.
Sorry, not last time. 270. 270.3.
270.3, good. And so now we just need to multiply that, right? That's grams per mole. And so now multiply 270.3 or so times 0.05. And so we get about 13.5 grams there to make our solution. So dissolve 13.5 grams of our iron 3 chloride hexahydrate there. Excellent. So right now you guys are almost ready to work in the stockroom basically. All right, let's try this one. So same sort of thing. So how many liters of a 0.125 molar sodium hydroxide solution contain 0.255 moles of sodium hydroxide? All right, so what do we get for this one? What's a good way to solve it too? Personally, I kind of like the proportions for this one. So 0.125 moles over liter, again, right, just following the definition of molarity. And so setting up a proportion, that again seems to be the easiest in this case. So solve for x. And so right, just cross multiply and divide. So 0.125 divided by 0.255. Oh, I did that wrong. I knew I did that wrong. Sorry. 0.255 divided by. And so, yes, I agree with the chat. X is 2.04 liters. You could also set up your dimensional analysis. So again, 0.125 moles over 1 liter. We want to get out liters. So let's divide. So go the other way, right? Just using dimensional analysis. So then starting with 0.255 moles, then we want to get to liters. And so now, right, flip your conversion factor. So 0.125 moles on bottom, 1 liter on top. We'll get our same answer there. Questions on that one? All right, so that's the first style of problems, right? So how do you go from kind of your solid material to then diluting it and making it a solution? Or again, getting the appropriate amount out. But then something else, the other thing that the stockroom does for us on a very common basis is they dilute solutions. So again, like we mentioned, we have the 15 molar nitric acid. We probably also have either, again, it's going to be anywhere from 12 to 15 molar solution that you buy. And that's of your hydrochloric acid, nitric acid, and then they have to dilute it to the appropriate amount for us. And super easy, so like I said, I like this chapter because it's really summed up by this formula. So C1V1 equals C2V2, where we just solve for whatever concentration we want initially versus our desired concentration, and then, right, plug in the appropriate volume. So depending on whether you're trying to make a final amount, then you'll solve, right, for how much of the concentrated one you need. And then what's super nice is this formula is general for all situations. So we're really focusing on molarity in this case, but it could be used with like percent by weight, it could be used with any other units. So our volume could also be in milliliters, just as long as it's consistent. So I'll say units don't matter, but just consistent. So that makes sense, right? So we could be in gallons and gallons. It doesn't matter as long as it's the same, right? Percent by weight, doesn't matter as long as you're consistent within your problem. So that's really nice. So it's a good general formula. And so let's look at how to properly make it. And this is just a little reminder. So we might see this as just M1V1 equals M2V2, but again, right, just know that the more general formula works as well, so you're not restricted to molarity. And so this would be an example of a dilution. And so looking at our situation, so we want 3 liters of a 0.5 molar calcium chloride solution, and let's just say we have 10 molar stock solution. And so the first thing you do before you start pouring stuff is, well, let's double check our calculations and figure out how much of our stock solution we're going to pour out. So C1V1 equals C2V2, and then again, just be consistent. So I'll just call this C1 and V1, doesn't really matter. And then our stock is going to be C2. So we're solving for V2, right? Again, how much of our original stock there. Then we can set up the algebra. And again, units don't matter as long as they're the same. So we have 0.5 molar times 3 liters. is equal to 10 molar, and we're trying to find V2 there. And plug it in now. So 0.5 times 3 divided by 10. So now that gives me 0.15 liters, or 150 milliliters. And so now that's what they're doing down here. And so now we're showing how to properly dilute it. And ideally you'd want to use something very precise, but as precisely as you can. Again, ideally you probably want to use a volumetric, but in this case they use a graduated cylinder. Measure out 150 mils, put it into our volumetric flask, and again, right, we'd be using now a 3-liter volumetric to get it to the appropriate volume. And then I'd probably dilute it a little bit, shake it around, and then take it again all the way to the 3-liter mark very precisely, and then again shake it, make sure it's all homogeneous and well mixed. Questions on this? So like I said, if you want to work in the stockroom, having this knowledge is super important, and you would need it. And of course, right, if you're a working chemist too, you would need that on a daily basis. You're going to be doing molarity, stoichiometry calculations. All right, let's go over this section a little quickly, because we've kind of seen some of these things before. We're just kind of putting it together again. And so this is reminding us of how things dissolve. So like we kind of covered, so salt water was an ionic compound. So we said that it disassociates in solution. So think back to the light bulb demo. And then sugar water, right, we saw how that was a molecule, so it's a discrete structure, so it does not disassociate. And you remember that with the light bulb, right? Nothing happened. And so then this just reminds us again of our solvent-solute interactions and how it's going to be pulling that apart. And so that's also why your salt water, you can get more dissolved into water versus sugar. And so again, it dissolves. And sugar does have, I think we've looked at the structure. You can kind of tell from our formula, but it does have, right, little alcohol groups on it. So yes, you can get sugar in to water, but it does take, right, some effort, some heating. And you guys probably know that, right? I'm sure you've tried to sweeten something before. Sorry, trying to find. Let's look at glucose. So again, right, it's got these little OHs. So I expect it to be somewhat soluble in water. And you guys can tell me about your experience in it, right? You gotta kind of stir it, give it some kinetic energy to try to get it to go in. Or that's often why recipes call for preparation of simple syrup, right? Heat it up, get it nice and soluble in that case. Versus, again, right, the salt water, ionic compound, so you can get a lot more into water. And so this, again, starts to get into solubility, at least a little bit more details, and the actual kind of why. And so we'll revisit solubility later in terms of KSP and actually like quantifying it. But again, this is just kind of telling us why things are, and then, right, you guys can experimentally look up the solubility for each individual substance you're interested in. And again, we've kind of seen that. And so once our solvent-solute interactions, as long as it overcomes our solute-solute, then we have dissolving. And again, we've seen this picture. It's good to see it again, right? Burn this into your brain if you haven't already, just emphasizing how water is polar. And we have our oxygen N that has our partial negative charge, right? Red electron density showing us as a region of electron density. maybe even fill in those lone pairs. Again, just emphasizing not only is oxygen electronegative and pulling the electron density towards it, but it also has those lone pairs. And then our hydrogens with our partial positive side. And so we've seen this, so kind of, again, skipping over it, but re-emphasizing the negative part solubilizes the positive cation part, and then our positive hydrogen ends solubilize and surround our chloride. And I can always get back out the water models with the magnets if anyone wants to look at that again. But we kind of saw that, so that's kind of a recap. And again, just a recap, just reminding us, okay, so that's why salt was the electrolyte. Again, we saw that. It disassociated, right? It lit up the light bulb. It was super bright. And that's why sugar does not. So again, sugar does not disassociate. And so that's, again, our term. Non-electrolytes are anything that does not disassociate. And I probably misspelled disassociate. And so again, just emphasizing the molecular interactions. So the solubilizing interaction versus, right, there's still solvent interactions. So yes, again, right, you can get sugar into water, but we're seeing why it doesn't go as easily. And again, why you can get a lot more sodium chloride in water versus sugar. So we still have interactions, right? It still solubilizes, but it's not disassociating into ions. And again, just kind of re-emphasizing that anything that's a strong electrolyte completely disassociates. So again, our ionic compounds, for the most part, will be classified as this, right? We expect everything to disassociate fully. We can start thinking into those like de-icers, right? Or the salt for the road. So as the temperatures slowly get colder, right, you'll probably see people salting. And so part of that half is, right, how many ions does it disassociate into, so that kind of dictates how good things are at solubilizing. Or if we do the lab this year that we did last year, we could think about other ways to extend it. So like if you've made ice cream by hand with like the salts, if you change the salt depending on how many ions it disassociates into, right, the kind of the more cooling power it has. So salting the roads, so all that's kind of coming. And then the weak electrolytes, so if you remember from the demo that I brought in 2 weeks ago or so, the weak electrolytes, the example that we saw was vinegar. So these are usually our weak acids, or organic acids tend to be this way. So many organic acids are weak. And again, it has nothing to do with how burning it is, but rather whether it disassociates. And so looking at this equilibrium, that's technically the wrong arrow. So obviously I just copied it somewhere, so it should be this double-headed half equilibrium arrow there. So again, just showing that some percentage is disassociated while some is together. And again, we're going to get there. We're going to quantify this later, starting in second semester here. So kind of see what's coming down the pipeline. And then again, right, most molecular compounds that dissolve in water but do not form ions are our non-electrolytes, which, like I said, is most molecular compounds. And so then this also touches into kind of acids and bases. And so we've kind of, again, just kind of jumped around with our acids. But for example, hydrochloric acid is a strong acid because it completely disassociates. I could get out my light bulb again. I think I did with the acid, right? You remember that? So I had the strong acid, and we saw how bright the light bulb is. And again, versus the acetic acid, where it did not light up my light bulb that impressively since it's weak. So again, that partial disassociation. And so just reminding us of our light bulb there. All right, that's a good place for a break. So let's take a 10-minute break. We'll be back around noon. And then we'll keep practicing with our now solution stoichiometry. So kind of putting everything together now. So stoichiometry and solutions.
You're like,
Taking notes from the board and have like been taking notes. Can we use those?
Yeah.
It's not. I think the first one.
Because I don't like rounding out. It's not how much is in.
I wonder if I do these right on the left. I was just asking Gabe about it. He thinks that I might have this backwards. And I'm not sure, because I'm like struggling with the little stuff, but it's slowly coming.
To me, it looks correct. Yeah, I think it looks good.
Okay, cool. Alright, I'm good.
You're right. I have a thousand. This one's supposed to go, I put this team to three. Last time I just went, finish all that. I took this one out.
Yeah. It's easier usually. Writing that.
So you're reading that? No, just the, you know, like the little bit of past them. Actually, I never really want to be in my, I saw it.
Yeah.
Yeah. The major or? Yeah, I know, I mean, like, you just watch those two teams. I use, 2020, my favorite, so. That might be our.
5?
Or like noon.
Oh, wow. Okay.
Huh? I think it's chaos.
from break?
Maybe.
Maybe. Did we lose anybody?
I don't know if I'm here.
All right, so let's continue as long as we all made it back. And so just like we did a bunch of stoichiometry calculations last week, we just want to do something very similar, except now, right, we have molarity as a different flavor in there. And again, right, just moles over liters of solution, so set that up for your relationship. It also lays out, again, the dimensional analysis that you can multiply it by your volume, and that cancels out, right, to give you moles there. And just kind of, again, right, in general, what we're doing, you start with some volume, we have to find moles, then probably, right, go back to our balanced equation, mole-mole ratio, moles of B, and then back to volume potentially, right? And so let's try that. Back out just a hair. And so now we're looking at this equation here. So we're reacting potassium chloride with lead nitrate to do a precipitation reaction. And so it asks us what volume in liters of a 0.15 molar potassium chloride solution will react with a 0.15 liter solution of 0.175 molar lead nitrate. So see if you can start that. So probably figure out how many moles you have of lead. And then you are given a balanced equation. So let's start going through it. And so again, right, the first thing I would suggest is, so it's asking us to figure out how much potassium chloride, right? But first we need, so let's find our moles of our lead nitrate first. And so I'll take our suggestion, so we'll do 0.175, and I'll rewrite it as moles per liter. And let's just figure out, again, how many moles are in 0.150 liters of this. Now just multiplying. then that gives us moles. So 0.02625 moles. And again of our lead nitrate. And so now looking at our balanced equation, they're in a 1 to 2 mole ratio. And so I would just do that. Again, you can set up a proportion. I'll do a little dimensional analysis. So now let's go. So let's find moles then of potassium chloride. And again, just looking at your balanced equation. So for every 1 mole of lead nitrate, we need 2 of potassium chloride. And so just multiply times 2 there. And again, that's how many moles we need. So 0.0525 moles of potassium chloride. And so now we want to go back to volume. So we're given our molar amount. And so we could, right, do some dimensional analysis. And so again, if it's 0.15 moles, so divided by our molarity, so moles per liter. So we can figure out our amount. And so we get, right, 0.35 liters. So 350 milliliters of potassium chloride solution there. Questions on that one? We all get that? Excellent. So let's try some more, or let's look at some other situations where we would need to do some stoichiometry. And so at some point we'll do a titration in this class. And so generally we have these titrations, so it could be acid-based, but you can also do other types of titrations as well, just as long as you have some sort of defined endpoint and then some way to monitor that endpoint. And so most commonly we do these acid-base titrations, and you of course need some indicator. And so the endpoint is when your indicator color is reached. And so typically you do this acid-base titration. So you have your base in what's called your burette here. So you have, this is your burette, and this allows you to accurately measure in the amount of liquid that you're dropping in. And so you would add it in, and right, your indicator would be here. So typically we use phenolphthalein, and so that's our acid-base indicator, so we can tell when we go past our equivalence point. And so the equivalence point is relevant since it's where our acid and our base then are a 1-to-1 ratio, or at least, right, in the sense that they've neutralized each other out. So this can get a little tricky if we have like a triprotic acid, because then that would mean we need like 3 equivalents of base to neutralize that acid. But again, basically they're neutralized. And so that's what it looks like. So let's try a sample problem of how this would look. And so we have a titration of a 10 milliliter sample of hydrochloric acid of an unknown concentration, requires 12.54 milliliters of a 0.1 molar sodium hydroxide solution. So what is our unknown concentration? And so before you start doing anything, I would just write out your balanced equation to verify everything that we stated. And so, right, we have HCl, so it just has one proton, so it's a monoprotic acid. And so here we can see right there in a 1-to-1 ratio when they're fully neutralized. I'll just write our equation. All right, so see if you can go from there. So what is our concentration of our unknown hydrochloric acid solution? So let's start going through this calculation. And so again, right, let's start with what we know. So we have our amount of sodium hydroxide solution, and we have the concentration. So let's find our moles of sodium hydroxide. And so we're given our 0.1 molar solution. So I'm just rewriting that as moles per liter. Then we can multiply it by this amount, and again in liters, so times 0.01254 liters to give us moles. And so then, oops, dropped my pen, we should have that many moles of sodium hydroxide. So 0.001254 moles. And again, 1-to-1 ratio from our balanced equation. And we're at the equivalence point, so all of this is neutralized. So that means we have 0.001254 moles of hydrochloric acid. But then we want the concentration. And so we're just about there, right? We have moles. We're given, it was a 10 mil sample. So now to get our concentration, we can just plug this in as 0.001254 moles over our amount in liters. So 0.010 liters. And so then we get a molarity of 0.1254 molarity there. Did we all get that? Yeah, question?
Are you able to do it like the C1, B1, C2, B2? Because I got the same answer doing it that way.
Yeah, so the reason why it worked is because they are in a 1-to-1 stoichiometric ratio. So that does kind of work for that trick, but just like double check in your brain, right, as to like why that works. So yeah, it's totally appropriate to make shortcuts, but again, right, that worked because they were in a 1-to-1 ratio. Of course, you could kind of scale it if you needed to with like the C2, C1, B1 stuff, but Yeah, so just be careful when using that. But excellent. 0.1254 molarity. Other questions, comments? So let's just try. Let's do another practice. So yeah, I stole these practice problems. Everett Community College has these posted as practice worksheets. That being said, right, if you look at other resources, the answers, I believe, are incorrect that they posted it, so just kind of be careful. So let's try to go through this one. It's a good practice here, kind of combining everything. So we're looking at this reaction, and so see if you can, right, name the type of reaction, and then go ahead and start number 2. So how many milliliters of a 0.225 molar bromic acid solution would we need to completely react with 3.26 grams of magnesium hydroxide? So then what type of reaction is this? So double replacement, that'd be one answer. And then chat has acid base, so I'll put both of those. So acid base or double displacement, neutralization. So good, lots of different ways to classify it. And so start walking me through what we're doing for 2 here. So what do we need to solve? A little loud out there. All right, so what do we do first? Kind of walk me through.
I'm bad with this, but would you find how many moles of magnesium hydroxide
Yep.
are there? 0.26 grams?
Yep, excellent. So let's start there. And again, how to earn points on your exam. Just start with your molecular weight of magnesium hydroxide. So what do we find for that? 58.319.
Someone else verify though, because I'm
Yeah.
really bad.
I actually don't have answers in front of my face either, so. Oh. Yeah, chat also agrees. Other people got, so yeah, make sure you got that. And so this is a good time to double check you got the correct formula for magnesium hydroxide. And so you can quickly see where things could go wrong potentially, right? Like writing the molecular weight, depending on the problem. So if I'm really mean on the final, I wouldn't give you this equation, right? I would just verbally say magnesium hydroxide reacts with hydrobromic acid. So you have to maybe potentially know some formulas. All right, so let's figure out moles. So divided by our molecular weight. Oops. And so then we get about 0.0559 moles or so. And thank you, chat, for double checking me. So 0.0559. So moles of magnesium hydroxide. And so then it's asking us for milliliters of hydrobromic acid. But first, let's check out our balanced equation. So again, we were given a balanced equation. I may not be so nice on the final. And so now let's do our mole-mole ratio. So for every 1 mole of magnesium hydroxide, we need 2 now of our hydrobromic acid. So 2 HBr. So multiply this times 2. And so that's how many moles. And we need milliliters though. And so this feels like a good time for a proportion. Again, you could continue with dimensional analysis. I just sometimes think proportions are easier to see for people. Is equal to, and we need 0.112 moles. And so now 0.112, so divided by, oops, what did I do? There we go. So about 500 milliliters or so. And again, double check me on this. It's about 500 milliliters of hydrobromic acid. Do we all get this? Excellent. Questions about that one? So again, pretty typical problem that you may face. And so now let's practice our types of questions again. So now we have 31.6 grams of magnesium hydroxide, and we're reacting it with 68 milliliters of a 0.725 molar solution. And so now thinking back, how do we figure out which one's our limiting reagent again? What did that mean? And then how many grams of magnesium bromide will be formed? So kind of think about that for a second. How do we approach that? So how should we approach this one? What do we need to do? Yeah, let's just find the moles of each and then compare, right, probably moles of product. And so yeah, I like that. Let's start with, so find moles of magnesium hydroxide, and then of course that'll in turn give us product. And so let's just start with that. So we already have some information. So let's just do 31.6 divided by the molecular weight we found, so 58.319 from earlier. So let me just write that out. And then, so we're given, so 0.5418 moles of magnesium hydroxide. And then we want to compare, though, how much product. So I would go back to our initial equation, and let's just compare magnesium bromide. And so they're in a 1-to-1 mole ratio. And so right now we can just, and I'm not writing it out just because it's 1-to-1, so that's pretty easy. So 0.5418 moles of magnesium bromide then will be formed. So did we all get that for the first one? And so now let's repeat that. So with our acid, so finding how many moles we have, so 0.725 molar solution, and we only have 68 milliliters, so converting milliliters to liters, and seeing how many moles that gives us. And so I get 0.0493 moles. That's already sounding small of hydrobromic acid. And then let's double check, right, our ratio. So it's a 2-to-1 ratio. And so now let's divide that by half, or use our dimensional analysis. So for every 2 HBr, get 1 product. All right, so now I'll divide by 2. So that's how much product we can form. And now we can say, okay, our hydrobromic acid is our limiting reagent. And again, we could only form 0.0247 moles of product. And so then the last part asks us how many grams of excess reagent will be left over. So see if you can determine that. I'll scroll back up, right? Use this information. So what do we get for this one? How do we find the answer? So what do we have from the previous problem too? So how much either product could we make, or how much hydrobromic acid do we have? So what do we find? What was this amount again? So amount of product, right? So let's just rewrite that for a second. So, okay, we had said that we could make 0.0247 moles of our product, so magnesium bromide. And so let's just start with that. And so again, 1-to-1 mole ratio. So if we can make that many moles of product, we need that many moles of magnesium hydroxide, right? And we could even, so there's a couple of different ways to do it, right? You also were given that you started with this 0.5418 moles, so maybe you can subtract moles minus moles, right? And then you could figure out moles of excess. You could convert this back to grams. You could convert, so let's just do this another way. So we said we need 0.0247 moles of magnesium hydroxide. So multiply that by the molecular weight we found. So 58.319, oops. So then we use only 1.43 grams. And so we could subtract, right, 31.6 now, minus that. So we're left with 30 grams of excess reagent. So 30.2 grams of excess magnesium hydroxide. But we could have also subtracted the mole amount, so 0.5418 minus this number of moles, and then multiply that by the molecular weight, and get the same answer, so then you're left with, again, 30 remaining. So a couple of different ways to get to that 30 grams of excess reagent. Questions on this one? So yeah, just more practice. Let's try some other ones. Let's do number 2 here. So how many grams of magnesium cyanide? So again, this is where I'm not going to test you on this explicitly, right? What's the formula for magnesium cyanide, but you might have to piece it together with the different cheat sheets and stuff you have. So that's where chemistry can get tricky. But how many grams of magnesium cyanide do we need to make 275 milliliters of a 0.075 solution? Sorry? Yeah. Yeah, triple bond, and it has a -1 charge overall, so you could balance it out. So how's this problem going? What do we need to do here? So what's the first thing we should solve, kind of given our information here? So we have 275 milliliters, 0.075 molar solution. So what should we find first? So moles, and again, right, we could do a proportion if that makes you happy. We can do our dimensional analysis, so either way. And then I also see, right, other things we can find. We can get our molecular weight of magnesium cyanide as well. And again, starting with the proper formula, so MgCN and then 2 of them. So hopefully you have cyanide on your polyatomic sheet. I try to get one that has most of them you'll encounter. So you can write the formula. And so somebody can give me the molecular weight of that. Otherwise, I'll set up our proportion to figure out moles. Oh, so 76.341 grams. All right, so let's double check that. Not that I don't trust you, just trying to get there. So moles, 1 liter, so 0.725 liters. And so 0.275 divided by 0.075. How does that look funny? Yeah, I feel like I did something funny. Oh. Sorry, I set that up wrong, that's why. So 0.275 liters on bottom. I knew that looked wrong. So 0.075 times 0.275. So then we should get that many moles, right? Does that look correct? So 0.020 moles of magnesium cyanide. And then did we find the molecular weight of that? Did somebody have this calculated? Was that this answer? 70? Oh, sorry. So 76.341. And so now multiplying this times our molecular weight now. And so that gives us our answer of 1.57 grams. Sorry, it's a little squished there. Questions on that one that feel straightforward? So again, just kind of think about that process, right? What you need to find. So generally you find moles of something. Oh, and then a question about rounding. So I would probably keep it at 1.57, at least what my calculator spit out. I got the 4 as the next digit, but if you did have 1.58, I wouldn't take off. I do expect, right, minor discrepancies with rounding, so that's fine. All right, let's see. Let's try, maybe let's do 7, a little bit trickier one. So we want the volume. We have a 0.75 molar solution, and we're trying to figure out what volume contains 39 grams of potassium hydroxide. So what are they asking for? What should you start with? What are some easy points on an exam? So how would we approach this one? What would I start with? So what did y'all do? You want to tell me? Yeah, you?
Oh, no, just,
What would you start with?
so you have 39 grams of potassium.
Yeah, and what's kind of the problem with that? Grams, right? What do we need?
In moles.
Yeah, so let's do that. Do you have the molecular weight of potassium hydroxide by any chance? Anybody got it?
56.105.
56.105. Does that sound correct? I see some nods. Excellent. So let's find moles first, right? Because I have no idea what 39 grams is. So 39 divided by our molecular weight, so about 56. And so we get roughly 0.695 moles here. And I'd probably, again, use a proportion. So we have 0.75 moles in 1 liter, and I want 0.695 moles. So how many liters is that? So divided by 0.75, and so roughly 0.927 liters. And good, so I'm seeing it in the chat just as I was about to say it, right? We only have 2 sig figs here, so probably want to round to 930 milliliters or 0.93 liters for the 2 sig figs. And again, right, could have minor discrepancies with rounding. So good there. Let's see, blah, blah, blah. Trying to see what other good ones we have. I think that's pretty much good for today. We could do another one of these, but kind of the same type of problems. So maybe we won't do 9 or 10 and 11 right now, but it just kind of walk through them mentally, right? Make sure that you can do all these calculations before you run out of here. So this one, it's asking for molarity, and just again, kind of repeat in your brain how you would do it. Just the process where you're given grams. So you want to find molecular weight of this, then get to moles, right? And then, divided by milliliters, or obviously convert that to liters, so 0.345 liters. So again, just kind of walking through that in your brain. And then 11 is just, again, emphasizing that you'd probably want a volumetric of this size, and then start by dissolving once you find the appropriate gram amount. All right, so we'll end there. But again, right, ask questions. Come see me this afternoon if you're struggling on anything. So I know we did this fast, but you should be in good shape if you can do, right, the stoichiometry kind of problems with this. So I'll go back to this one, but as long as you're kind of comfortable doing these calculations, so stoichiometry plus solutions, you should be fine. Otherwise, spend some time with it. Sweet. So yeah, you can just turn everything in there.
I emailed you my.
Sweet. Thank you. And then any last questions online before I shut the stream? Oh, stapler. So let me know if you have lab makeups. Yeah, that's fine.
Okay, should I turn that in online or?
No, just next week is fine. Okay, have a good Thanksgiving. Thank you.